If you think America is spending $52 billion to build microchip factories just to secure its electronics, you've been misled. The truth is far stranger and infinitely more dangerous. Right now, the United States is attempting the most expensive economic rescue mission in human history. Trying to rebuild an industry it voluntarily gave away 30 years ago. But here is the terrifying paradox. Even if America spends hundreds of billions, it might still fail because making a modern semiconductor isn't just manufacturing. It's bending the laws of physics at a cost that would bankrupt entire nations. So how did the most powerful economy on Earth become completely dependent on an island thousands of miles away? Just to power its cars, modern fighter jets, and artificial intelligence. And why is bringing this industry back home turning out to be almost impossible? Over the next few minutes, you are going to discover the hidden economic machine powering the modern world, where a single machine costs $200 million. A tiny speck of dust can destroy tens of millions in seconds, and where the real profit isn't made by the companies whose logos are on your laptop. To understand why everyone is suddenly fighting over microchips, you first have to realize what a silicon wafer actually is. It isn't just technology, it is the oil of the 21st century. Every smartphone, modern missile, electric car, and AI data center relies on these microscopic labyrinths of silicon. The global chip market is already creeping toward $1 trillion. Yet, remarkably, almost the entire world relies on just a handful of facilities to produce the most advanced chips on Earth. Think about that for a second. If oil supplies get disrupted, energy prices spike. But if the supply of advanced microchips stops, modern civilization literally freezes, car factories shut down, medical equipment can't be built, servers go dark, and the global economy loses trillions in weeks. That is the sheer scale of global demand today. But here's what most people completely miss. The market isn't controlled by the names you know best. When you buy an iPhone or an NVIDIA graphics card, you assume Apple and NVIDIA built the chips inside. But they didn't. In fact, Apple and NVIDIA don't own a single semiconductor factory. They are what the industry calls fabless chip designers. They draw the blueprints, and then hand them over to someone else to actually build them. And that brings us to the real kingmaker of the global economy, TSMC, the Taiwan Semiconductor Manufacturing Company. TSMC is a pure-play foundry. They don't design consumer products. They just manufacture chips for everyone else. By doing this, TSMC solved a massive economic dilemma. Building a modern chip factory is so insanely expensive that almost no single company can afford to build one just for itself. So TSMC pooled the world's demand under one roof. Today, TSMC manufactures over 90% of the world's most advanced semiconductors. One single company, on one single island. Which brings us to the central question: how does a chip factory actually make money? On paper, the revenue engine sounds simple. A client gives you a digital blueprint. You print millions of chips onto round silicon wafers, and you sell those wafers back to the client. But the financial reality behind this process is mind-bending. When TSMC prints a wafer for a company like Apple or NVIDIA, they aren't charging for raw materials. Raw silicon is essentially purified sand. It's dirt cheap. What you're paying for is microscopic precision. A single advanced 8-inch wafer can cost upwards of $20,000, and a single modern fab processes tens of thousands of these wafers every single month. That translates to billions of dollars in revenue pouring out of a single building every quarter. However, this isn't where the real money comes from. The real profit driver in chip manufacturing isn't raw volume. It's something called yield rate. Imagine you run a factory that bakes 10,000 microprocessors onto a single slice of silicon. When you test them, only 60% of them actually work. The remaining 40% are dead silicon, total trash. That 40% failure rate can instantly destroy your profit margins. But if your engineers optimize the manufacturing process so that 95% of the chips work, your production costs stay exactly the same, while your sellable inventory skyrocketing. This hidden yield rate is why incumbents like TSMC dominate. Every wafer they process teaches their algorithms and technicians how to reduce errors. The more you produce, the higher your yield, and the higher your yield, the lower your unit costs become. It creates an unbeatable economic flywheel that crushes potential competitors before they even start. But that is only part of the story. Because to get those yields, you have to buy the most complex machines ever created by human beings. Enter ASML, a Dutch company that holds an absolute monopoly on the world's most critical manufacturing tool, extreme ultraviolet lithography, or EUV. Without ASML's EUV machines, nobody on planet Earth can make state-of-the-art AI microchips. Each machine costs well over $200 million, requires 13 cargo planes just to ship, and uses lasers that blast microscopic drops of molten tin 50,000 times a second to create ultraviolet light. This single piece of machinery represents the highest barrier to entry in human history. If you want to build an advanced semiconductor factory today, you don't just need capital. You need to stand in line for years just to buy equipment from a single Dutch monopolist. Now, let's look at the brutal cost structure that makes U.S. manufacturing such a high-stakes gamble. When you build a modern semiconductor facility, or fab, you are not building a regular factory. You are constructing one of the cleanest environments on planet Earth. A single speck of dust inside a cleanroom is thousands of times larger than the transistors being printed, meaning a floating piece of dandruff could ruin an entire multi-million-dollar batch of wafers. To prevent this, these cleanrooms require continuous air filtration systems, giant concrete foundations sunk deep into bedrock to eliminate ambient vibrations from distant highways, and massive water purification plants that filter millions of gallons of water every day to near absolute purity. The price tag for just one advanced fab? A staggering $15 to $20 billion. To put that into perspective, building a modern semiconductor fab costs more than constructing a nuclear aircraft carrier. And here is the catch. That investment depreciates at a terrifying rate. Technology moves so fast that a multi-billion-dollar facility becomes obsolete in just 5 to 7 years. That means a chip manufacturer must run their factories 24 hours a day, 7 days a week, 365 days a year, just to pay back the initial capital expenditure before the tech becomes completely outdated. Every single minute a fab sits idle, it burns through tens of thousands of dollars in pure cash loss. This is why the semiconductor business scales so ruthlessly. Small players simply cannot survive. The initial fixed costs are so astronomically high that you need massive volume just to break even. Once a chip maker reaches massive scale, their cost per chip plummets, creating an economic fortress that protects them from outsiders. And that brings us to the multi-billion-dollar dilemma facing the United States today. For decades, Western nations outsourced chip manufacturing to Asia because labor was cheaper, construction was faster, and environmental regulations were less strict. Asia built vast supply chain ecosystems where chemical suppliers, specialized component makers, and elite engineers all lived within miles of each other. Then came the realization: America had completely lost its manufacturing edge. If a crisis ever cuts off Asian chip imports, Western economies would collapse in a matter of weeks. So the U.S. government passed the historic CHIPS Act, pouring over $50 billion in subsidies to incentivize giants like TSMC, Intel, and Samsung to build megafabs on American soil. In places like Arizona and Ohio, it sounded like a masterstroke on paper, didn't it? But here's what most people completely miss: throw money at a problem, and you quickly realize money isn't the only thing missing. Building these facilities in America has run straight into a brick wall of reality. Construction costs in the U.S. are up to 5 times higher than in Asia. Project approvals take years longer, and environmental regulations slow down progress at every turn. But the biggest bottleneck of all isn't money or regulations. It's human capital. Running a semiconductor fab isn't like running a standard manufacturing plant. It requires thousands of highly specialized technicians and engineers who are willing to work grueling 12-hour shifts inside full-body cleanroom suits, monitoring nanoscale machinery with zero room for error. In places like Taiwan, this workforce was cultivated over 40 years. In America, That specialized labor pool barely exists today. When TSMC started building its massive fab in Arizona, they immediately faced severe labor shortages, cultural clashes between foreign management and local workers, and endless delay after delay. And this creates a massive economic paradox. Even when these US fabs are fully built, the chips produced inside them will likely cost 15 to 30% more than identical chips made in Asia. So who pays for that premium? Will tech giants like Apple, Nvidia, and Tesla willingly accept lower profit margins just to buy American-made chips? Or will those costs be passed directly down to you, making future smartphones, laptops, and electric vehicles significantly more expensive? This reveals the ultimate truth about the semiconductor industry. Economics always triumphs over pure politics. You cannot simply write a check for $50 billion and expect to rebuild a fragile, highly specialized 4-decade-old supply chain overnight. Yet, the race is far from over. As artificial intelligence explodes across the globe, the demand for computing power is accelerating at an exponential rate. We are entering an era where AI models require millions of specialized chips working in tandem, driving demand to levels never seen in human history. Fabs are already pushing past 3-nanometer and 2-nanometer production lines. At these scales, transistors are so tiny that electrons literally begin to leak through barriers due to quantum physics, forcing engineers to invent entirely new materials and three-dimensional architectures